Alright, well, we got snowed out today, I suppose, so I will make this video to make up for our lost time. Hopefully we'll be on track. So we've reached section 14.7 Dummett and Foote, which is of course on solvable and radical extensions, leading to the insolvability of the quintic, and so I won't prove everything in here, but I'll try to at least sketch the proofs of the more important aspects of it. So here's the first definition. The extension k over f is said to be cyclic if its Galois group is a cyclic Galois group. All right. Then there are two propositions which are given to try to describe this, which are sort of the linchpins of this section, if you will. I mean, anyway, they hold everything together in terms of the later constructions. First of all, proposition 36. Let f be a field of characteristic not dividing n, which contains the nth roots of unity. Then the extension of f adjoining the nth root of a for some a and f is cyclic over f of degree dividing n. And so again, the proof is in Dummett and Foote. I won't go through that at the moment. And then proposition 37, any cyclic extension of degree n over a field f with characteristic f not dividing n, which contains the nth roots of unity, is of the form f adjoining the nth root of a for some a and n. Now, this sort of extension is called a simple extension. A simple extension, well, a simple radical extension, I should say. A simple radical extension is one where you take the base field and adjoin one nth root. All right. So the proof of proposition 36 and 37 is somewhat interesting, and maybe we'll spend some time Wednesday on it. I don't know. It involves something called Lagrange's. Oh, what's it called? Just a second here, I'll tell you. So the proof involves this Lagrange resolvent, which is kind of interesting, and some neat and pretty, not that hard to follow calculations. So that's it might be worth looking at Wednesday when we're together. I don't know. Anyway, and there's also a remark here, which is perhaps interesting. If we were to adjoin, say, a bunch of nth roots, I don't think those all have to have the same n, do they? Oh, yeah, they do. So if we were to adjoin a bunch of nth, I mean, later in this section we look at adjoining roots with different index, not all n, they like n1, n2 to ns, as it turns out. Anyway, so this, if we join nth roots of these k elements, then this is an abelian extension, and it has group exponent n. The group exponent is a power that if you raise anything in the group to that power, you get the identity. So anyway, you might wonder where the n comes from. It comes from, this is just a continuation of the discussion of the proof of proposition 36 and 37. And anyway, he indicates that the study of such extensions is the start of what's called Kummer theory, which he comes back to in a later chapter. In fact, what chapter was that? Well, it's the one Jonathan was thinking about possibly doing his project on. I don't know. We'll see whether or not Jonathan picks that, but kind of an interesting tie into something I was talking to Jonathan about the other day. But anyway, it's a little bit of a digression, so let's get on here with it. So this is the big definition. What does it mean for a polynomial to be, solved by radicals? All right, that's really the technical realization of the thing I've claimed from the start of the course, which is that this whole course leads up, well, this part of the course, at least the story arc in the course, leads up to the problem of when you can or cannot find a formula to express the zeros of a polynomial equation in terms of roots and combinations of roots, if you will, of the coefficients. And so this makes that idea precise. And in particular, we can talk about an algebraic element of f, all right, is expressed by radicals, or can be solved of in terms of radicals, if alpha is an element of k, where k is a field obtained. It doesn't have to be a simple radical extension, but it has to be the result of a tower of simple radical extensions, all right, so one after the other. There's only finitely many of them, right, because it's an algebraic element, which means that the extension is finite degree over the base field. But anyway, each one of these extensions is accomplished by adjoining the nth root of a sub I. All right, at each level we have a simple radical extension. And such an extension field over f is called a root extension of f. A polynomial, f of x, can be solved by radicals if all of its roots can be solved by radicals. In other words, if all of the zeros of the polynomial exist in a root extension, then it's solvable by radicals. Here's an example which is a little bit harder than the ones we typically look at. So the base field's the rationals, then adjoin the square root of 17, then take that field and adjoin twice 17 minus root 17, all right, and then adjoin twice 17 plus root 17, and then adjoin a3, which is more complicated. There you go. And so at each level, the thing you're adjoining, right, this is a tower of radical extensions, right? Each time we're just adjoining the square root of an element in the previous, well, I could say base field, but it's not quite the right terminology. The thing before it in the tower, anyway, the subfield which we're extending. So it's always adjoining a square root at each level. So each one of these extensions has degree 2, which means in total, I guess this is a degree. We count 1. That's 2. 2, 2, 2. So what is that? That's degree 2, degree 4, degree 8, degree. I think this is degree 16 over the rationals. And of course that ties back to our previous section where we talked about, if it's an extension of the rationals, the degree 2 to a power, that corresponds to the fact that, the only way that that extension could correspond to a constructible number, right, is if it has that 2 to whatever power degree extension. And it's not an accident. This tower of extensions came up in the construction of the 17 gon. So anyway, that's a kind of interesting tower of radical extensions, which is, I think, a little bit harder than the ones I'll probably actually ask you to work out. Goodness gracious. And then that leads us to Lemma 38. Right. So just give me a second here. Get my cheat sheet out. So the thing is, he says, in considering radical extensions, we're on page 6, the end of 627 at the moment. In considering radical extensions, one may always adjoin roots of unity, since by definition, the roots of unity are radicals. All right. This is useful because then cyclic extensions become radical extensions, and conversely. In particular, we have Lemma 38. Lemma 38. If alpha is contained in a root extension k, then alpha is contained in a root extension which is Galois over f, and where each extension, ki plus 1 over ki, is cyclic. Now, and then he says that this k is the same notation as we were just using in the definition. So in the definition, k appears as the top of a tower of fields, each one being a simple radical extension of the previous stage. The k is a root extension. So he doesn't really mean that each extension like that is cyclic. That's not what he means, I don't think. He means that once you play games with the nth roots of unity, or in this case n sub ith roots of unity, once you throw those things in, then this composite, you take the tower you're given, you sort of repackage it by adjoining roots of unity. After you do that, then the corresponding sort of full tower, if you will, that's the one that you have the cyclic quotients. So the basic trouble is if you're missing roots of unity, then it kind of spoils things. So you have to throw in the roots of unity to make things work. And so here's the argument, a sketch of it at least. He says let L be the Galois closure of f. Then for any automorphism, f fixing automorphism of L, we have this, if we feed the given tower of subfields, well, we can, obtain a corresponding tower of the permuted, the conjugate subfields, Galois conjugate. And in particular, if we look at the quotient of sigma ki plus 1 with sigma k, it's going to be a simple radical extension. Why? Because this sigma ki is generated by this guy. Oh, I'm sorry, that is supposed to be... think this is supposed to be I plus 1. Is generated by sigma the nth root of a sub I, which is a root of... Hey Hannah, I need you to stop talking unless there's a reason you need to be talking, thanks. Which is a root of x to the ni minus sigma of ai over sigma of ki, like that. So in other words, that is a radical extension of sigma ki. Whee! But then Dummenfeld argues that the composite of two root extensions is a root extension, and so the composite of all conjugate fields, sigma k, for any sigma in Galois is again a root extension. So we can adjoin to f all the n sub ith roots ranging I equals 1 to, I think actually s minus 1, if I'm more fussy, of unity to form f prime. And then, so if we take the composite of the original tower with the f prime, which is basically f with all the nth roots of n sub ith, n sub 1, n sub second, n sub third, n sub, I guess n sub n minus 1, n sub I minus 1th, roots of unity that your heart's desire, well then this is yet again a root extension. And moreover, that's Galois extension, since it's the composite of Galois extensions. And both the original extension of f prime over the base field, well, those are both, that's a composite of radical extensions, so it's a cyclic extension by our previous lemma. That will be a proposition 36 or 37, I forget which one, but and then that is also cyclic because it's Galois, I think it was. Let's see here. So I think the root extension to start with doesn't have to be Galois because you could be missing roots, right? So you're possibly missing roots to the polynomial, so it's not a splitting field. But by joining the nth roots of unity, you elevate it to a splitting field, and so it's a Galois field, you know? Rather, it's a Galois extension. Anyway, this cyclic, that cyclic means that putting it together in total is cyclic because, and getting to the point here, this f prime composed with k. Keep in mind, this is the field which is built from products of things in f prime and k, right? It's the natural way of combining two fields to get a larger field. And there's a section we unfortunately skipped. Let's see what. Actually, we actually, this is where the rubber hits the road, and me skipping section. I'll tell you here for a second. I mean, you know, I guess the bottom line is to really cover this chapter, I need to devote probably about 3 more weeks of class, to be totally honest to you guys. But the section 14.4 on composite extensions and simple extensions, there's proposition 19 and proposition 21. Both of these are meaningfully used in this, you know, section 14.7. Proposition 19 says that if we have Galois extension k over f and f prime over f is any extension, then the composite field kf prime over f prime is a Galois extension. So that's exactly what we're using here, that proposition 19. And then later proposition 21 concerns another thing about composites, but we'll get to that when we get to it. So I'll leave that aside. So anyway, here it is, Lemma 38. And so then that brings us to the next definition, which you might say should be covered in Math 421, but I can't remember if I did this last year or not. Anyway, here it is. A finite group is solvable if there exists a chain of subgroups, and so here's the deal. Starting at the trivial subgroup, which we'll say the S1, and the S minus 1th contains that as a subgroup, and then all the way up to the I plus 1th is contained in GI, and then all the way until we get to the 0th one, which is G itself. So you have this chain of subgroups leading to G, where each quotient, GI by GI plus 1, is cyclic. All right? This is said to be a solvable group. And the reason for that terminology becomes really, really obvious by the end of this lecture. Now there's theorems you can prove for solvable groups, and these to me feel like excellent test questions for you guys. Just saying. So theorems for solvable groups. The subgroup and the quotient groups of solvable groups are solvable. So we had some homework problems like that in 421, right, where we took a group with a particular problem and then proved that subgroups and quotient groups of that group had that particular, not problem but property. You know, and then the other direction is sort of like constructing things. So if we have H as a subgroup of G and the quotient both have a particular property, then G itself has that property. I think of that as kind of like as a constructive comment, right? So this is saying if you kind of like take apart pieces of G or squash pieces of G to 0 or the identity, then you still have that property in the looking just at the piece or looking at the sort of well, the quotient, of course, but this is the other way. So if we have the subgroup is solvable and the quotient is solvable, then that implies G is solvable. So solvable groups it's a fairly nice property for groups. It behaves, but these are the two central sort of theorems for solvable groups. Anyway, that leads us to finally the big point here, which is this is Galois theorem, Galois connection between solvable polynomials and solvable groups. It simply says this: polynomial f of x can be solved by radicals if and only if f of x has Galois group which is solvable. And let me at least sketch the proof of that. So again, here it is. Polynomial f of x is solved by radicals if and only if the Galois group f of x is solvable. This is theorem 39, page 628 and 629 of thumb and foot. Assume f of x can be solved by radical. Then by lemma 38, each root of f of x is contained in an extension which is a root extension over f. But then, by proposition 21, the composite L of such extensions is a root extension. This proposition 21 is in that section we skipped, so sorry. But I do think I've shown you guys enough that you could, with a little bit of work, you could understand the proof of proposition 21. It's certainly within your grasp. You guys are all capable of that. So anyway, the composite of extensions is, again, a root extension, and if we let G sub I be the the subgroups of the Galois group which correspond to G sub I, in other words, rather K sub I. In other words, K sub I is the fixed field of G sub I, right? Then we have, by the fundamental theorem of Galois theory, the Galois group of the extension of Ki plus 1 over Ki is the quotient of the fixed, the groups, corresponding groups, Gi over Gi plus 1, part of the fundamental theorem of Galois theory. And as K is a root extension, we have that these quotients are cyclic, right? But that proves, of course, that G is solvable. So that's of course why we're calling a solvable group as a solvable group, is because under the Galois correspondence it corresponds to a solvable extension, right? I mean, that's why solvable groups are just called solvable groups. The other direction, if we have a Galois group G of f of x is solvable, and suppose K is a splitting field for f of x, then we can look at this tower of, this chain of subgroups, right? And, I think I was supposed to put, I forgot my counting here, G sub 0 rather. Oopsie. And so if the Galois group is solvable, then that means that we have a chain of subgroups where the quotient of each is cyclic, right? And of course we can look at the splitting field, and in that splitting field we have to have a chain of subfields corresponding. These appear as the fixed subfields of the given chain, right? And of course the inclusion reversing property means that the splitting field corresponds to the trivial group, right? And vice versa. The whole group corresponds to the base field, and everywhere in between reversed, right? In particular, the fundamental theorem of Galois theory again says that the quotient, the Galois group of the extension Ki plus 1 by Ki is equal to Gi over Gi plus 1 is cyclic. Now, let's see here, why is that? Well, this is because again, we're assuming that the Galois group is solvable, right? Suppose that the group is solvable, right? So we're assuming that these are cyclic this time. Let's see, how did I know they were cyclic last time? It was because I'm sorry, I may have said it backwards last time. I'm sorry if I did, but what I should have said last time if I didn't in my It's sad I can't remember, but we knew that this was cyclic because that was a radical extension. We're using those initial propositions 36 and 37 that say if it's a root extension, then it corresponds to a solvable Galois group, basically. Root extension implies that that it's a cyclic extension. Anyway, sorry. Getting back here, so we've assumed that the Galois group of f of x is solvable. Gave us this chain of subgroups. Look at the corresponding subfields. We have that each quotient is cyclic because we're given that the Galois group was solvable. And that means then that this is a cyclic extension. And then you can, again, take your base field, throw in all the roots of unity that your heart desire, get the corresponding tower of subfields that have all of the needed roots of unity in it, and that's going to give you a root extension. And therefore, we have shown that there exists, this extension of f in which f of x can be solved by radicals, because this has, this has all the roots of f of x, and it's appearing as a radical extension over the base. So, if I have somehow muddled the proof, I am sorry, but it is quite clear on page 628 to 629. So let me try to rescue this lecture with corollary 40, which I think I have a pretty good understanding of. The general equation of degree n cannot be solved. Make sure I'm not off the page here. Cannot be solved by radicals for n greater than or equal to 5. The proof is simple. The proof is solvable? No. For n greater than or equal to 5, the group Sn is not solvable. This is a chapter 4 thing, actually. So it's like, this is an easy thing to say. It's a harder thing to prove. If you go back, this is this would take you a couple of hours of gory calculation to really deeply understand why Sn is not solvable for n greater than or equal to 5. Anyway, so that's a chapter 4 result. Hence, by theorem 32, which we proved, we mostly worked this out. This is that the general polynomial of the Galois, the general polynomial has Galois group equal to the symmetric group on n elements, right? And so the general polynomial is essentially just, what we're saying is, look at an nth order polynomial, do not impose any of the particular details relating the coefficients of the polynomial. If you don't take advantage of any of the particular details of how the coefficients are related for a given f of x, then what you're left with for the Galois group is an embedding of Sn in the automorphism group, right? As we discussed, over characteristic not zero, that's not possible. Like, there just are relations between the coefficients which are implicit from working over a finite field. But for characteristic 0, this is a plausible thing. Of course, then the theorem 39, which I almost just proved, in other words, that the Galois group of is solvable if and only if it's a solvable f of x. Well, so we've got this insolvable group for n greater than or equal to 5, and we've got f of x is solvable if and only if the Galois group is solvable, so consequently, you can't find a general solution for f of x equal to 0 in terms of radicals if n is greater than or equal to 5. In other words, the quintic and higher analogs of the quadratic equation simply do not exist for generic polynomials. For specific polynomials, of course, you can find possibly can find the roots in terms of radicals in a radical extension built from the radical formula built from the coefficients of the polynomial. And his exercise 21 shows you just how complicated describing when that is or isn't possible. If you look at exercise 21 in this section, there's a formula that's about a half a page, maybe two-thirds of a page long, where that thing describes when it is or isn't possible to find a formula for the quintic in terms of radicals. It's quite awful. And apparently is from a paper that I think Dummett wrote. Anyway, here's an example given in Dummett and Foote. It's a good example. So here we have x to the 5th minus 6x plus 3. This is irreducible by Eisenstein with p equals to 3, right? Because 6 and 3 are divisible by 3, but 3 is not divisible by 9. So thus the splitting field has degree So it's irreducible fifth order. That means the splitting field has degree divisible by 5, since adjoining a root of 0 will give us an extension to degree 5. It follows that the Galois group G has to be a subgroup of S5, and that the order of the Galois group is divisible by 5, which means that apparently the Galois group contains a 5 cycle. Because it has to, by the way, permute the roots of this irreducible polynomial. That thing we were quibbling over at the end of last class, that's actually at the start of this previous section. At the very start of it, it explains that why irreducible polynomials, if you look at the Galois group acting on an irreducible polynomial, it acts transitively on the roots. So we shouldn't have worried. I mean, that's in the start of the last section we were worrying about that. But anyway, I digress. But we argue G also contains a transposition. If you have a 5 cycle and you have a transposition, which is a 2 cycle, you can generate all of S5. All right, that's a fun fact of permutation groups. So why does the Galois group contain a transposition? Basically, the transposition is complex conjugation suitably restricted. To see this, we use a little calculus. He points out f of minus 2 is minus 17, f of 0 is 3, f of 1 is minus 2, f of 2 is 23. So pictorially, it's something like this, right? And so we have these 3 crossings. That gives us 3 real roots for sure. However, there can't be a 4th one because the derivative of this is 5x to the 4th minus 6. And I believe that has 2 real roots. It does not have, I think that's probably got 2 real roots. Is that right? Let's see here. Increasing, decreasing, increasing, so 2 zeros. I think it actually has 2 real roots. It doesn't have 3 real roots, which is what you'd need. You need the derivative having 3 real roots if your polynomial had 4 real roots, because that would mean if it had another root, it would have to have another turning point, right? And so to have another turning point, you'd have to have another 0 in the derivative, which we don't have because it just has 2 real zeros. So there do not exist 4 real roots for f of x, but the fundamental theorem of algebra says that it does have 5 complex roots, and of course the other pair have to be a conjugate pair because the original polynomial is over the rationals, right? So the product of x minus alpha 1, x minus alpha 2, x minus alpha 3, x minus alpha 4, x minus alpha 5 has to work out to x to the 5th minus 6x plus 3. So it follows that the alpha 4 and alpha 5 I was just mentioning have to come in a complex conjugate pair. So I just said alpha 4 is equal to alpha and alpha 5 is equal to alpha bar. And the thing in the Galois group, the automorphism that's a transposition, is simply the one that sends alpha to alpha bar and fixes the real roots. Well, that is in fact something that sends roots to roots, so it's in the Galois group, and it's easy enough to see that that corresponds to a transposition in S5, and consequently that shows that the Galois group of this guy is S5, which means that these alpha 1, alpha 2, alpha 3, alpha 4, alpha 5 cannot all be found in that the splitting field for this polynomial is not a root extension of the rationals. Which again is tantamount to saying that you can't express the roots in terms of sums and differences and of radicals of radicals of radicals of radicals. So I think that's kind of neat. Now let me tell you what else is in this section. What comes next, of course, is they then turn their attention to the actual description of what are the cubic equation. So he looks at the solution to the cubic equation by radicals. That meaningfully involves Lagrange's resolvent that I didn't go over the proof of today because I didn't go over the proof of proposition 36 and 37. We didn't see anything about that, but the solution that he presents, of Cardano's formulas, he uses the Lagrange resolvent and some calculations to come to the to derive the formula for the cubic in terms of the Lagrange resolvent, which gives you a taste of the old Galois theory, right? The Galois theory that existed before group theory was more completely understood by mathematicians, which of course is beautiful, complicated, and would be a lovely way to spend a couple hours. But there it is on page 630 to 631, and he has a specific example working out the Cardano formula on page 632, which is kind of neat. And then a rather interesting calculation on page 33 to 34. So he shows why it is the case that the cubic formula necessarily involves complex numbers. So, I mean, he supposes that, suppose you had a irreducible cubic and it had 3 real roots, and that were possible to express one of these roots by radicals involving only real numbers. He then, does this argument, and he is able to prove that it is impossible to express the roots of this cubic in terms of real radicals only. So it shows the necessity of the complex number system to study solutions to cubic equations over the rationals, which is, that's a very interesting chapter here in math history. Then he turns his attention to the quartics, and it's, so we can reduce the quartic to the cubic, and in so doing, find a formula in terms of things we already done in terms of the cubic. It's, so there's that. And then the rest of this chapter, so section 14.8, he turns to the more computational techniques for Galois groups over the rationals. Really gets into how you look at cycle types and so forth. And then section 14.9 is on transcendental extensions and separable extensions, infinite Galois groups, which is kind of the next chapter in the story, the one we don't actually get to in this course. And of course, there's always more to learn about Galois theory. We just scratched the surface of things in here. Really, I'm just giving you, I would say, a survey of Galois theory, not really a proper treatment of it. But anyway, I hope you've enjoyed what we've done. Wednesday, most likely I'll probably turn my attention to differential Galois theory, and I'll show you that calculation that my brother provided in terms of extending the rationalization trick using Galois conjugates, which I think is really, really pretty. So anyway, guys, enjoy the snow. Thanks.